webinar hosted by the South African Institute of Physics. I'm Rudolf Erasmus from Wits University, and I'm also the SAIP council member responsible for the webinars. Now, the purpose of these webinars is to communicate on a wide range of topics to the broader physics community in South Africa and beyond. And today's presentation is by Dr. Sibaliso Mhlanga. The question and answer session will take place after the conclusion of the webinar. So if you could please hang on with your questions, or you can, during the presentation, you can already put them in chat if you want. And then there will be opportunity to answer those questions after the conclusion of the presentation. So Dr. Mhlanga is a postdoctoral fellow at the University of Cape Town and the SA Alice Consortium at Itemba Labs. She completed her doctoral degree at UCT in 2020 and also did her MSc at the same university, working on an Alice physics research topic. Her physics journey started at the National University of Science and Technology in Bulawayo, Zimbabwe, where she studied her honors in applied physics. She is also the South African representative for the junior scientists at Alice, and she's involved in mentoring honors, MSc, and PhD students at Itemba and UCT. She is passionate about outreach, particularly in high energy physics. So it's my honor to request Dr. Sibaliso Mhlanga to present her webinar entitled Charmed, Where to From Here. Thank you very much. The floor is yours. Please proceed.
Okay, thank you, Rudolf. Good afternoon, everyone. I would like to thank the organizers of the webinar for this opportunity, and I would like to thank you all for sparing me time to present this to you. So, as Rudolf has already said, the title of my talk is Charmed, Where to From Here. So, we know that quarks are the smallest building blocks of matter, and that quarks never exist alone in nature. They are always found in combination with other quarks or antiquarks to form large particles of matter, which we will refer to as hadrons. And so quarks form triplets called baryons, such as protons and neutrons, as you can see from the picture here, or quark-antiquark pairs, which we refer to as mesons, which are shown examples here, the pions and the kaons. And there are also four fundamental forces that act between the quarks, namely the strong force, the electromagnetic force, the weak force, and the gravitational force. So the force carrier of the strong force is the gluon, and the gluon is responsible for binding quarks and antiquarks, or quarks and other quarks together to form these hadrons. So quantum chromodynamics is the theory of strong interactions between quarks and gluons. And quantum chromodynamics predicts a phase transition from hadronic matter to a deconfined platonic medium. When I refer to platonic medium, I refer to quarks and gluons collectively. So they are collectively known as platons. So this quarkonic platonic medium is also known as the quark-gluon plasma, and it occurs at very high temperature and energy densities. And the quark-gluon plasma is expected to have been the state of matter in the early universe, around 10 to the power 6 microseconds. So this quark-gluon plasma can be produced and studied in the laboratory by means of ultra-relativistic heavy ion collisions. So in these collisions, what happens is the heavy ions are accelerated up to very high relativistic energies. And as you can see here, instead of them appearing as spherical as we know them, they they appear as flat disks due to the Lorentz factor, which and the in the plasma, and as they do so, the system reaches thermal equilibrium. And once the system reaches thermal equilibrium, it begins to expand rapidly. And as it expands, it cools down, and then we begin again to form hadrons. So this stage of the system will be continuous, interactions continue, and the expansion also continues until we reach chemical and kinetic freeze out. And when we reach this kinetic freeze out, it means that all the particles that are formed are now fixed, and these are the particles that stream into our detectors, and we can actually measure them. So heavy quarks are an important part of these experiments because heavy quarks are produced very early in the collision during the initial hard scatterings. So by heavy quarks, I refer to charm and beauty quarks. So it means that they experience the full evolution of the system. So if the quark-gluon plasma is formed, the heavy quarks will live before and during and after the formation of the quark-gluon plasma, studying heavy quarks produced in the systems. For example, the heavy quarks can lose energy in the system via gluon radiation and collisional mechanisms, and they also tell us information about the quark-gluon plasma because they participate in the collective expansion of the quark-gluon plasma and thermalization thereof. And also we can study various hadronization mechanisms that occur because heavy quarks hadronize in two ways. Either they be high PT heavy quarks, which then hadronize by breaking into smaller hadrons, or they hadronize via coalescence, where low PT heavy quarks will usually combine with the light quarks or gluons to form these hadrons. So one of the ways that we can actually study this the QGP is via the nuclear modification factor. So the nuclear modification factor refers to the modification of the transverse momentum spectra of the heavy quarks in with respect to PP collisions that are scaled by the collisions, which is the RAA, is 1 if there are no nuclear effects present. However, if there are effects of the hot and dense QCD medium, which is the quark-gluon plasma, the binary scaling that we use to make the heavy ion similar to PP is broken, and the RAA is not equal to 1. So if RAA is less than 1, we have a suppression, and if RAA is greater than 1, we have also the energy loss of heavy quarks is different from the energy loss of light quarks and gluons. So there is a mass hierarchy of the energy loss, which then also translates into a hierarchy in the RAA. So further insight into the transport properties of the medium is provided of heavy quark hadrons with respect to the reaction plane, of which geometric ions participating in the collision is converted by the interactions among the medium constituents to a final anisotropy in the transverse momentum space of the produced particles. And this effect can be characterized by the elliptic flow, which is V2, which is the second harmonic coefficient of the Fourier expansion of the particle azimuthal distribution. So this V2 of heavy quarks at low PT carries information about the thermalization and participation of the collective expansion of the heavy quarks in the collective expansion of the QCD medium. And then at high PT, the V2 measurements can constrain the path length dependence of the in-medium energy loss. And this path length dependence is different for collisional and radiative energy losses. So, as my title already says, charmed, where to from here? So I'm going to concentrate on these two phenomena on the results of measured by Alice in charmed hadrons. So charmed hadrons are basically hadrons containing at least one charm quark. So they are characterized by a decay length of around 60 to 300 micrometers from the interaction point. So we also have baryons which are a combination of three quarks. So the Large Hadron Collider is where all this, for these collisions, is the Large Hadron Collider. So the Large Hadron Collider is between Switzerland and France, and it is a 27-kilometer ring, and it's located 100 to 150 meters underground. So it has 4 major experiments around the ring at the interaction point. So we have CMS and Atlas, and then we have LHCb, and then today I'm going to be discussing ALICE, because ALICE, which is a large ion collider experiment, is the one that is dedicated heavy ion detector on the LHC, and is designed to study the properties of the QGP, which is what I introduced already. So a closer look at ALICE. So this is the ALICE detector. And then the ALICE detector consists of the central barrel and the forward muon spectrometer. And here I just show different detectors that we use for triggering, for vertexing and tracking, and also for particle identification. So for charmed hadron reconstruction, we use the invariant mass analysis to obtain the raw yields. So this channel is actually a golden channel for reconstructing charm, because the other channel that we have is the leptonic channel, which has a branching ratio of around 10%. However, this one has a branching ratio that is very big, around 55%. So these are the decay channels that we usually look at. And for today, I'm going to be discussing prompt charged charmed hadron reconstruction, prompt charmed hadrons and non-prompt charmed hadrons. So prompt charmed hadrons are charmed hadrons that come directly from the collisions, and then they decay into other particles. And non-prompt ones are charmed hadrons that come from the decay of a B that has come directly from the collision. And then, so this non-prompt charmed hadron can also be an indirect measurement for the B hadron. And then the other concept that I want to discuss before we go on to the results is the concept of centrality. because now when we look at heavy ion collisions, we need to consider also the geometry of the collision. And this is quantified by the collision centrality. So the centrality of the collision depends on the impact parameter. And the impact parameter tells us how far apart the centers of the two colliding nuclei are. So if the impact parameter, if the centers are close enough, the impact parameter is small, and then we have central collisions. And in a central collision, we have many participants, and we have many collisions. Then we also have a peripheral collision, where we have the distance between the centers of the colliding nuclei being very large, and the region of overlap is small, and we have a large impact parameter, few participants, and this one will give us peripheral collisions where we have mostly spectators. So the other way to quantify the centrality is using the percentile of the cross-section. For example, lower percentile like 0 to 5%, 0 to 10% will be for most central collisions, and around 30 to 50% will be semi-central collisions, and then around 70 to 100% will be peripheral. It will be semi-peripheral and peripheral collisions, sorry. So now I'm going to discuss the first result of charmed hadron RAA. So in this result, we have lead-lead collisions at 5.02 TeV, and we have the sum of the charmed mesons D0, D plus, and D plus star, D star plus. And the measurement is the nuclear modification factor, which I said will be the yield in lead-lead collisions with respect to the yield in PP collisions that are scaled to the number of binary collisions that we measure in lead-lead collisions. So the results are presented in different centralities. So the red one is 0 to 10%, which is most central, and 30 to 50% is semi-peripheral, and 60 to 80% is peripheral collisions. So what we see is that, before I forget, I have to mention that it's also the first measurement where the charmed meson spectra has been measured down to close to 0 PT in lead-lead collisions and central, in most central collisions. So what we see is that we have a large suppression at low to intermediate PT, and it is larger for most central classes than for the peripheral ones. And then the second results that I have here is the RAA in central collisions of 0 to 10% of the lambda C, which is a baryon, and then the average D0, D plus, and D star plus, which are the charmed mesons, and the DS is also a charmed meson, and these are compared to charged particles. And what we see is that the quark mass and color charge dependency that I showed you is I talked about earlier is quite evident, especially at low PT. So we see a mass ordering where the suppression of charged particles is bigger than the suppression of the charmed hadrons. And then also what we see is at high PT, this is not the case. We see a similar suppression in all in both the charmed hadrons and the charged particles, which might actually speak to an interplay between the PT spectra of charm and light quarks and gluons. And then lastly, the lambda C, as you can see, the lambda C is the black one. It hints to a very small suppression, which confirms the role of coalescence for baryon states, which tends to enhance the lambda C production in lead-lead collisions. And then now to charmed hadron, RAA, in comparison with models. So the RAA of charmed mesons is compared to several model calculations with different ingredients and actually different schemes for the implementation of heavy quark transport and hadronization mechanisms and radiative and collisional processes for energy loss. So what we see is that the models that contain fragmentation and coalescence and both radiative and collisional processes generally provide a better description of measurements at low and high PT. And then the next measurement is the V2 or the elliptic flow of charmed hadrons. So here the elliptic flow is measured for semi-central lead-lead collisions, which is around 30 to 50%. And we see a positive V2 for charmed hadrons, similar to pions, yes. It's similar to pions at high PT, which confirms that we have strong interaction of heavy quarks with the medium. And it also supports the idea that charm quarks participate in the expansion of the QGPA. And then lastly, we have a comparison between between the models in V2 and RAA. And this comparison is important because we can actually achieve a stronger discrimination power of data over models. And if the models are doing right, we should be able to describe data in V2 and RAA simultaneously in the whole range of PT. However, as you can see from the results, the models provide a fair description of data in some PT regions, and it is very challenging to provide a simultaneous description over the whole range of PT. So this would be very useful for an improved constraint of the medium transport properties modules, which is one of the main goals of the future prospects of the data that we're going to be collecting in Run 3. We need to provide constraints to theoretical models for the whole range of PT for V2 and RAA simultaneously. So I have spoken about the measurements that ALICE does in heavy ion collisions, which is the main goal of why it exists. However, I've spoken a little bit about PP collisions, where I said we need the PP spectra in order to compare with the PLED spectra, and then we scale this PP spectra by the number of binary collisions. However, we also do PP measurements to provide constraints for PQCD calculations, and we also do PLED collisions, which serve as a control experiment to tell us what kind of initial state effects to expect when we introduce a lead ion in the collision. And this helps us to disentangle the cold nuclear matter effects that exist as a result of the modification that occurs in the nucleus before even the collisions occur. And then we disentangle from the modifications that occur as a result of the quark-gluon plasma. So here I'm showing two results: the nuclear modification of charmed mesons in P-lead collisions, and the nuclear modification of charmed mesons in lead-lead collisions. So I showed the lead-lead one as a function of PT earlier. So in this one, as I just explained to you, that P-LED helps us to disentangle initial state effects from the final state effects. So what we see is that if we have modification in P-LED of the D mesons, then it means we have to take them into account if we see modification in lead-lead collisions. However, what we see here is that the RP-LED of charmed mesons is consistent with that the strong suppression that we see in lead-lead collisions is due to final state effects. So it's due to the nature of the quark-gluon plasma and how it interacts with the charmed mesons. So in summary, and the observations that I presented so far, so I presented about lead-lead collisions, and what we have seen is a strong suppression of charmed hadron production in central lead-lead collisions, and we saw a mass ordering of RAA observed at low to intermediate PT, and the RAA is described by models with different implementation of charm quark energy loss, hadronization via coalescence and fragmentation, as well as hydrodynamic expansion of the medium. And then we saw a positive charmed hadron V2, which is evidence that heavy quarks participate in the collective expansion of the system. And we also compared the models, how the models perform in RAA and V2 simultaneously. And at the moment, we see that we are unable to provide a description of data in the full PT. So the models are not able to provide this description. And then in P-LED collisions, we saw that the RP-LED for charmed mesons is consistent with unity, which confirms that the suppression of charmed mesons seen in lead-lead collisions is due to final state effects, which are effects of the presence of the quark-gluon plasma. So what lies ahead is that ALICE is undergoing an upgrade, and these results that I presented here were mainly for run 2, and we are going on to run 3, and at the moment is commissioning, and then we are going to have new detectors, and the highlight is the new inner tracking system and the new forward tracker. We could only have charmed mesons measured in the central barrel, but if we have the muon forward tracker, we'll be able to resolve charm and beauty separately. Then it means we have measurement for comparison with the central barrel as well as the forward muon spectrometer. And then what we expect in future for run 3 is that we'll have an improved charmed meson vertexing, especially at low PT, and we'll have precise measurement of charmed mesons and baryons at an increased luminosity. Thank you.
Well, thank you very much for that presentation. Much appreciated. The floor is open for any questions. You're welcome to type something in the question and answer or chat box, whichever is available, or also raise your hand if that option is there. From experience, that usually takes it's a very straightforward question. When is run 3 scheduled to start?
At the moment is commissioning, and things are changing very fast with this COVID and stuff, but I think it's second half of 2022.
Thank you. Seems like you've answered all the questions people might have had.
Okay.
Questions immediately. I'm sure people can contact you via email if they do have questions afterwards.
Yes, yes.
Thanks very much again for your excellent presentation. Much appreciated.